what is this talk about? So there are a few quotes by Boole that are frequently given in the literature and frequently mentioned about this idea of uninterpretable expression. So in his investigation of the laws of thought, so from 1854, Boole wrote that the validity of a conclusion arrived at by any symbolical process of reasoning does not depend upon our ability to interpret the formal results which have presented themselves in the different stages of the investigation. So you do some computation, you do not need to be able to interpret what you have during your computation, as long as you get to a result that makes sense. In brief, at least that's how it's usually read. So he said, so that one can go through intermediate steps which are not interpretable to a final result which is interpretable. And infamously, he gave as an example the employment of the uninterpretable symbol square root of -1 in the intermediate processes of trigonometry. As a kind of strong statement in the philosophy of algebra, this is regularly mentioned, it is read in a maybe somewhat incorrect way with respect to Boole's own practice. And this is what I want to explain here. So first, to explain what the problem is, I need to say a few words about how Boole's algebra of classes, or algebra of logic, as it's sometimes called, works in the basics. So within a given universe of discourse, this is the term Boole uses. Boole uses letters to denote classes, what we might call sets today. So it's not classes in set theory. And then if you have two classes that you write X and Y, you can write what we would call their intersection. So the class of elements that are common in X and Y by the product or juxtaposition of letters, X, Y. So this, we would write the intersection maybe. X plus Y defined only if the classes are disjoint is what we would call the union of the two classes. But note that this is only defined if the classes are disjoint. X plus Y is not defined initially if the classes are not disjoint, have elements in common. X minus Y is the difference. So you take away the elements that are in Y from the elements that are in X. And you have 1 as the universe and 0 as the empty class, so that 1 minus X is the complement of X. Here I'm using Boole's algebra of classes as it is in the laws of thought. Some differences with his previous work, but that do not matter here. Okay, so on this basis, Boole offers a general algebraic method for solving reasoning problems. I will not get into that here too much. The point here is that this method involves manipulating and transforming equations as in algebra, but with some puzzling features. First, so I've already said, Boole defined addition X plus Y only for disjoint classes X and Y, not if the classes are not disjoint. Yet his manipulations sometimes go through steps in which addition is used between classes that are not actually disjoint, and likewise for subtraction. So this is one thing that might seem a bit strange. Also, Boole did not initially, at the beginning of the laws of thought, define division between classes. He did not say which class an expression such as X over Y was supposed to represent. Yet his general methods require division and even go through apparently baffling expressions such as 0 over 0 or 1 over 0. So many readers, and it's quite natural actually, have identified these two features with the uninterpretable expressions that Boole mentions in his methodological remarks. As a result, what we get is a view according to which Boole's logical methods involve uninterpretable expressions, his expression, in two ways, because plus and minus are sometimes used between classes that do not satisfy the relevant restrictions. And here I want to give some quotes to make the strongest case I can for this, kinds of things that you can find Boole writing. He says, the expression X plus Y seems indeed uninterpretable unless it be assumed that the things represented by X and the things represented by Y are entirely separate, so it's two disjoint classes. So that's the first. This is a Boole quote. Yeah, sorry, I deleted the page number of the laws of thought, but this is from the laws of thought. Everything that's in italics and in block quote is a quote. or between the quotation mark. I do not make a distinction between mention and citation. So because
we had a long discussion when he wrote his dissertation about that.
So that's the first reason. And then second reason on this view is because if we use an operation of division that is never given an interpretation at all in the laws of thought, at least. This too seems confirmed, at least if you read quickly, by Boole himself, who in one instance wrote of the equation z equals x over y, that it is not at present in an interpretable form, and then he continues computing with it. Okay. So a typical assessment of this kind of view of what Boole is doing is the one you find in Michael Dummett. This is a review of publications on Boole from the 50s. There is not in Boole's system any restriction on the formation of terms of the forms x plus y and x minus y to such combinations as may be interpreted by direct appeal to the rules of interpretation, which he explicitly states. And in formalizing logical inferences, he regularly transforms equations in which no such uninterpretable terms occur into equations in which they do occur, and these in turn into equations in which they do not. This procedure, says Dummett, obviously stands in considerable need of justification. So he says this is not rigorous at all. And similar things about division that I will not show you here. Okay. Associated with this reading is the idea that in order to rigorously explain how Boole's mysterious procedures, or apparently mysterious procedures, can be successful, we need to supply the missing interpretation. So we need to say what the symbols refer to at each step of the calculation. So I'm just giving you the gist of the best known one to give you a sense of the way this has been done. Although there are other ones. This is the one by Theodore Hailperin, originally from 76, I think. This one uses signed multisets. So formally, what this means is that to each element of a universe of discourse, you will associate an integer, positive or negative. So it's like having a function from u to the relative integers. And then, so how does this work? Well, if you have your universe of discourse here, and you have a certain class here, X, well, the elements that are in the class will have be associated with 1, and those that are not with 0. It's pretty straightforward. So you give them values like this. So any multiset in which each element has multiplicity either 0 or 1 straightforwardly corresponds to a class. The universe, well, you give 1 to every element. The empty class, you give 0 to every element. And then if you do this, in this setting, you can interpret all the expressions of Boole's calculus. So here I'm leaving division aside. He has a more complicated treatment of division, but this already gives you a sense for how this has been approached. So why is that? Well, if you have X here, and then maybe we will consider another one, another class here, Y. Okay, then what is X plus Y? Well, elements that are either in X or in Y, but not in both, you will be able to associate the value 1. And elements that are in both, well, you can just add their values. And you can say, well, this element has multiplicity 2, and this one still has multiplicity 0. And you can also have negative multiplicity. So you construct this kind of formal gadget, and then you can say, well, X plus Y, if they're not disjoint, well, you'll just have some elements that are counted multiple times. They have a multiple multiplicity. And so every element can be assigned a multiset. Some of them will be classes, some of them will be something else where you have multiplicities, but you can interpret everything.
In means that if you call it what you call 2A in the sum, there is twice A.
Yeah, or here it's a set theoretic kind of construct here. So you can associate this thing.
But then 0, 1 are no more the Boole meaning. 0, 1 are no more the empty set of the universe.
Well, why? Because why do you think that? Because 1 you still interpret as ascribing 1 to everything.
Okay.
0 is and then you have elements that are, so basically you can immerse the classes into the multisets. Every class can be associated with to a certain multiset, but then you have more multisets than classes, and you can interpret everything. Okay. So, this is kind of the idea. Well, we want a method where, every sub-expression, we want to know what it means. Maybe here, this can't be associated with a class, but we can associate it with something else in which the elements are counted twice over. You can do the same thing for subtraction. That gives you the idea, and then division is kind of complicated, but on the basis of this, you can do things. So that's kind of how this has normally been approached.
This is an Hailperin invention, or there is some basis in Boole work?
I mean, it's a way of justifying or a way of giving a semantics to Boole's calculus. Yeah. I think the earliest thing that you could really say is a hint of that is in De Morgan, who says, well, the elements are counted twice over. Peirce kind of gestures to it. Venn makes various remarks that he thinks, actually, in some sense, maybe you can interpret it, but it's a numerical interpretation where things are counted multiple times and so on and so forth. This is the first time it's been made formal in this sense. But if you want to look for predecessors, I guess you could do that kind of thing. Okay, so what do I want to argue here? Actually, what I want to say is that this kind of reading is largely incorrect because it relies on projecting onto the text of Boole a modern notion of what it means to interpret symbolic expressions. So you want each each sub-expression to have an interpretation, and then you want the global interpretation to be determined compositionally from the bottom up. But this is not how he uses the word. And then after that, I will explain this more. I will turn to his philosophy of algebra. And reassess claims that are related to this reading of Boole that see him as a kind of instrumentalist. You just play with the computations and then you see what you get. Okay, so the first part is really looking at the text and some of the manuscripts of Boole and trying to make sense of the way he actually uses the words interpretation and interpretability and what he does with it. First, I want to point out that even in the quotes I've given you, you should start to be suspicious of the way we are reading these interpretation and interpretable. I've given you 2 quotes earlier. The expression x plus y seems indeed uninterpretable unless it be assumed that the things represented by x and the things represented by y are entirely separate. And then also the equation z equals x over y is not at present in an interpretable form. Well, here you can see that he doesn't say is interpretable. He says it seems uninterpretable. He doesn't say the equation is not interpretable. He says it's not in an interpretable form. And these are actually substantial nuances. And if you look throughout the text, you will find all kinds of qualifications like this. He talks about expressions being immediately interpretable, independently interpretable, being in interpretable form, and so on and so forth. There's not one notion of interpretation, but many. And that's what we need to make sense of. Moreover, more anomalies, and this is usually mentioned, but the full consequences of it are not usually discussed. He made claims such as all equations are interpretable in logic. So any equation in his calculus you can interpret, even if they are fractions and so on. So something more than interpretation in what we think he means, the sense we think he means is involved here. So at how he uses these terms. First, perhaps we need to backtrack a little bit and get a sense of what a symbolic calculus for Boole is. Here, as he phrases it in the laws of thought, but also elsewhere, basically, a calculus is defined from what he calls literal symbols and the laws of thought, basically letters, X, Y, Z, and so on. Signs of operations, so plus, times, and minus, and so on. So you have initial symbols, then you have signs of operations. And then symbolic calculus is defined by some relations or laws. And what he calls laws are actually, we might call them equalities, equations, general equalities, such as x plus y equals y plus x, or z times x plus y equals zx plus.
The identity there means that the object on the right is the same as the object on the left, or does it mean you can transform the form on the left and the form on the right?
Well, I think it's closer to the second one, but he doesn't say that. But we'll get to that. Yeah, it's definitely more in line with the second one you've said. So what we might call commutativity and associativity, commutativity and distributivity. And then fundamental to his view of algebra is that one and the same calculus can be interpreted in different domains. So this is a quote from the beginning of his first work of logic, not the laws of thought. The validity of the processes of analysis does not depend upon the interpretation of the symbols which are employed, but solely upon the laws of their combination. So laws of their combination here are the things like those equalities I've shown you, x plus y equals y plus x, and so on. Every system of interpretation which does not affect the truth of the relation supposed is equally admissible, and it is thus that the same process may, under one scheme of interpretation, represent the solution of a question on the properties of numbers, under another, that of a geometrical problem, and under a third, that of a problem of dynamics or optics. I should make a little remark here. In this talk, I really focus on Boole rather than on surrounding people who defend somewhat similar views. Here, the immediate point of reference is Duncan Gregory, and usually the formulations of Duncan Gregory are the closest to Boole's, but I don't want to enter into the similarities and differences here. So we'll keep to his own formulations. So you have different interpretations, and so at this stage it seems very familiar. One might think it's like an uninterpreted formal language that could then, or an uninterpreted theory maybe in a language that then could admit different models, different interpretations of different models. So so far it seems familiar, and indeed Boole continues to say that his calculus in the laws of thought admits of two such systems of interpretation. First, a logical one, in which the literal symbols, so x, y, and so on, are interpreted as classes, so sets, and plus, times, and so on as operations on classes. And a quantitative one, in which x, y, and so on are interpreted as either the number 0 or the number 1, and plus, times as the usual operations on numbers. So here, I just want to point out, be careful. So in the quantitative interpretation, if x and y are both 1, x plus y will be 2. So the letters have to be 0 or 1, but the rest can be normal numbers, at least in the laws of thought. So you shouldn't think Boolean algebra, Boolean things of the modern mathematics. This is something a bit different. And here you just have the normal operations on numbers. It's not 1 plus 1 equals 0 or 1 plus 1 equals 1. It's a number. It's a quantitative interpretation. It's just that the literal symbols, the letters, can only be assigned to either 0 or 1, but complex expressions can be any numbers. It's just one interpretation of the calculus. It's not the Boolean algebra kind of terminology is a misnomer, or at least it can create misunderstandings. Okay, so so far, it might seem very familiar. It might seem like just what we do in logic, compatible with, we have an uninterpreted calculus, then we could set up a model, and then we could interpret an expression by giving interpretations to the variables, and then compositionally assigning interpretations to expressions. This might seem familiar. But And here's one important difference. For Boole, operations usually come with restrictions on when they can be performed. So, for instance, his aggregation of classes, which he denoted by plus, could only be performed on disjoint classes. I've said that before. What's crucial is that such restrictions are interpretation specific and not part of the uninterpreted calculus itself. So in the way he's thinking, you have a certain calculus, and there you have signs of operations like plus, times, and so on. And then it's only at the level of one particular interpretation that you might have restrictions on when you can actually perform the operations. For example, in the quantitative, but not in the logical class-based interpretation of the calculus of the laws of thought, the operation plus can always be performed. As I said, 1 + 1 = 2, 0 - 1 = -1. You can always do it. And if you have fractions, you can do it. At least so he claims. If you have a 1/0, maybe it's infinity. So he thinks you can always do it anyways. So for him, whether an expression is interpretable will depend upon the system of interpretation chosen, and upon the interpretation of any variables in the expression, of course. So how you interpret x + y, well, are they numbers of classes? And then which numbers and which classes are x and y? And then you can know whether x + y can be interpreted, and if so, what its interpretation in terms of classes or numbers would be.
Yeah, but there is one thing. So in the interpretation of multiplication as intersection, we have,
there you can do it always.
So x times x is x. So the rules of algebra are not the same. So x power 2. What is the result of x power 2?
Okay, so
exactly
intersection.
Exactly.
I mean, this is anachronistic, but let's say, and in here, well, this is a letter, so we'll come back to this. So this can only be 0 or 1. 0 times 0, 1 times 1. There's no problem here. This is not a law for complex expressions. This will be crucial in what follows.
Okay.
But for literal symbols, they can only be 0 or 1. So logical interpretation, this is true. Quantitative interpretation, this is. All right. Now, I just want to point out that there's one thing that sometimes puzzles people in the secondary literature. Boole says, there's this uninterpretable symbol, square root of -1 in the intermediate processes of trigonometry. And sometimes you read, even in serious papers, it's weird, maybe he wasn't up to date with the literature and he didn't realize that you could give a geometrical interpretation to this. But this is missing the point. This is missing the point because interpretation is relative to what system of interpretation you have. So this comes up most clearly, although he discusses this in many places, but this comes up most clearly in his correspondence with Cayley, to ask how it is that x/2 plus x/2 = x in my system is the same as to ask how square root of -1 times square root of -1 = -1 in a system of pure quantity. For although you may interpret square root of -1 in geometry, you cannot in arithmetic. And likewise, Cayley, actually Boole is not understanding, I think, what Cayley is telling him, but Cayley explains how he thinks of complex numbers, and Boole insists, well, whatever you're saying, you're not giving a quantitative interpretation to square root of -1 in arithmetic. Maybe you're giving a geometrical interpretation, but if you're solving an arithmetic problem, this is about numbers. And you're working on numbers, then square root of -1 means nothing. Maybe if you're working in the plane, then it means something. If you're working on a geometrical problem, maybe you can do something with directions, but in arithmetic, you cannot. So the point is that interpretability is relative. So it depends on what kind of, it's not a question of the uninterpreted calculus. It depends on what your domain of interpretation is. And so he's not denying, it's not a general claim about square root of -1. He says, in specific contexts, you are solving an arithmetic problem. you cannot interpret it. So again, should pay attention to his qualifications here. It's in the intermediate processes of trigonometry. Actually, this refers directly to a paper by Gregory where he discusses this in the context of trigonometric expressions. So this is why this weird reference appears, I think. And this is the same for his logical calculus. X over 2 can be uninterpretable when solving a problem about classes, but interpretable in numbers. So 1 over 2, well, that's just half. That's not a problem in numbers. Maybe in classes, it doesn't mean anything because 2 doesn't even refer to a class in the first place. So that can happen. Okay. Now, what's going on? In this framework, I said restrictions on interpretation are not part of the uninterpreted calculus. They're only part of certain interpretations that you choose. So the uninterpreted calculus itself, as belonging to pure symbolic algebra, is independent of any interpretation relative restriction. So what does this entail? Here's one quote that I think is particularly straightforward. It's from a manuscript that's probably a few years after the laws of thought, but it's very consistent with the laws of thought. The datation is not quite certain. The equation x plus z minus y equals x minus y plus z, writes Boole, is perfectly intelligible and necessarily true when x, y, z denote numbers of which x is greater than y. And we can realize it or conceive it to be realized in the world of things in a variety of ways. So if x is greater than y, well, x plus z is greater than y. So you can do the sum of x plus z, and then you can take away y, and that's no problem. Likewise, if x is greater than y, well, you can take away y from x, and you still have something that makes sense, and then you can add z. His discussion assumes here that you have a priority to the left. He's thinking in the terms of the order in which you perform the operations here. And then the question is, are we permitted to employ the above equation as if it were true? That is, to substitute one of the forms connected by the sign equal for the other. So here he phrases it more as a rule of substitution, without such implied condition connecting the numbers x and y. Now, the method of algebra assumes that we may do this, that in the procedure of the intellect, the formal law is independent of the conditions of restrictions imposed upon its material realization. The result is always found to be the same as if the conditions of material realization had been attended to throughout. So if your uninterpreted calculus has this law, as he put it, then you can use it even if it seems that this introduces a violation of the conditions under which the operations can be performed, then you can compute doing that. And here's another formulation it's the one, or at least one of the ones, because there are many that you find in the laws of thought. For reasoning by the aid of symbols to be valid, it suffices that the formal processes of solution or demonstration be conducted throughout in obedience to all the laws that are determined from the interpretation of the symbols, but without regard to the question of the interpretability of the particular results obtained, as long as the final results can be interpreted. So you can follow these laws, even if, it creates a situation when maybe y is greater than x. And so if you do this transformation, then you end up with x minus y, even though y is greater than x, and you don't know how to make sense of it, but you can do that. He repeats this principle many times in many places. I'm calling it the principle of formal reasoning, or PFR, because I will want to refer to it repeatedly. Okay, so what does this entail for Boole's calculus? So on the face of things, it creates a lot of things that are uninterpretable. So just to give a small example, in his calculus, if you take x and y classes that are not disjoint, so you can't form the union, but then you take w such as wx and wi are disjoint. The intersection of w with x and the intersection of w with y are disjoint. You can always find a w that satisfies that. For instance, you take the complement of the intersection of the two. Then you write an equation like Z equals WX plus WY. That's something that you will typically have to do in many situations in Boole. There's no problem of interpretation on any way you understand what interpretation means. But Boole has no problem with freely using distributivity to obtain Z equals W times X plus Y. But here, X plus Y has not been given an interpretation as a class. And actually, Boole will do more radical things like divide out by W, for instance. And so here, it appears like just following the laws will create expressions that are not interpretable. So it seems. So this is how you easily get apparently uninterpretable expressions in his calculus. But in fact, I think it's more useful to look at this the other way around. In fact, what it does is make the very idea of what it means for an expression to be interpretable kind of murky. What do I mean? Since simple algebraic identities can transform apparently interpretable expressions into apparently uninterpretable ones and vice versa, what happens? Here I've given a quote by Venn, who is trying to explain this aspect of Boole in a later text. So I know this is kind of later source, but is clearly formulated. 2xy is unauthorized by itself, and therefore x plus y minus 2xy cannot, as it stands, be read off into strict logical language. But a different arrangement makes it irreproachable, for it can be thrown at once into the form x times 1 minus y plus y times 1 minus x. It then becomes x or y, but not both. And this is something where every sub-expression can be interpreted, and you can do the whole thing compositionally. This kind of arrangement, writes Venn, will often make an expression interpretable, which otherwise would not be so. Everything that's in color in quotes is my emphasis. Colors are from me. So what this means is that even expressions that look uninterpretable according to the standards of compositional assignment of classes could well be interpreted in some sense of the word, because you can transform them back. So you do it the other way around. If you start from this x plus y minus 2xy, well, maybe you can assign a class to the expression, but not from the bottom up, but by rewriting it. Actually, we'll offer a general procedure for doing that systematically when it's possible. And so that's one of his terminological subtleties is linked to this. Often he will say of such expressions that they are not immediately interpretable or not in interpretable form, because you need to transform them first before you can interpret them, like x plus y minus 2xy.
Sorry, I do not understand. If I understand well, a calculation cannot start for something that is not immediately interpretable. You start from something that is immediately interpretable. So then you apply a rule of transformation, and you get something that is not immediately interpretable.
Yeah.
But insofar they are algebraic rule, they are univocal. So if you go in a sense, you go also in the other sense. So this is obvious that I work in this way. But anything that is not interpretable can be made interpretable transformation exactly because it starts from something that is interpretation by a rule that can be inversed. Or not?
Not really. So, okay, so this is if you transform at the level of a single equation. Actually, what happens, I don't think I have it later in the slides. You can look at his method overall and see when you actually have difficulties, and he discusses this in chapter 10. What happens is that, for instance, at one stage in his method, you will have to add separate equations. And even if each equation is immediately interpretable in this terminology, maybe the sum won't be. And then you need to further transform it. And this is not really a reversible operation in a straightforward sense. So in the course of the method, you will produce equations that, and that is typical. Yeah, because you are doing things like adding equations. I mean, you know, I'm not even sure what it would mean to reverse it in this straightforwardly. It's not like applying an algebraic identity. It's a step of method where, okay. Okay, so before we proceed, we need to introduce another distinction that he's making. This one is more commonly discussed because he's very explicit about it. I want to point out that so far, interpretability, as we've mentioned it, is not a property of symbolic expressions in and of themselves. It depends what the symbols mean that appear in it. X plus y, you just if you just give me this expression and you ask, is it interpretable? I can only say, I don't know, because what is X, what is Y? Are they disjoint? Are they not? However, Boole works a lot with a notion of independent interpretability, which is a property of formal expressions. Here's his definition. By an independently interpretable logical function, I mean one which is interpretable without presupposing any relation among the things represented by the symbols which it involves. Thus, x times 1 minus y is independently interpretable, but x minus y is not so. The latter function presupposes as a condition of its interpretation that the class represented by y is wholly contained in the class represented by x. The former function does not imply any such requirement. So you can always do x times 1 minus y, but not the other one. So here you have this notion of independent interpretability. I just want to highlight, maybe to make sure there's no misunderstanding, that here Boole uses the word function. Actually, he uses it synonymously with expression, and he actually defines it like this. So it's not a function in the modern extensional sense of an arbitrary input-output relation. It's an algebraic expression in the things. And so whenever he says function, you have to think, I haven't even given values to the variable. It's just an expression built out of the elementary components. Yes.
A propositional function.
Yeah, you could say that. So the way I think I haven't given the
is a form.
Is a form, yeah.
It's like
Really better.
it is completely important in the English algebra. So that is simply a form. The function is a form.
Yeah. And that was standard. I mean, he says it explicitly because he doesn't want any misunderstanding. He says by logical function, I mean a certain expression built out from literal symbols using the operations. But so when he says function, it also emphasizes that it's the form and not, you haven't given values to the things.
Of 19th century, the standard in British, not even in France.
Not anymore in France, but
not anymore in France, but in Britain it is standard.
Okay, but so why am I bringing this up here? Is that for him, independent interpretability is the first notion he tackles and then gives a characterization of it that is invariant under algebraic transformation. So it does not depend on actually how the form is presented. And so that's kind of, you start from maybe x plus y minus 2xy, and maybe you could rewrite it as a, you just reinsert the thing, but do I actually have it? It doesn't matter. Oh, it's here. Doesn't matter for now. So now here he very explicitly will get to a characterization of independent interpretability that is a global property of expression, so to speak, and does not depend on whether you initially encounter it as this or as the other form. So to understand his characterization, let's backtrack just a little bit. So you've already brought this up, Marco. The literal symbols of Boole's logical calculus, such as x, satisfy the equation x squared equals x, because the literal symbols are meant to represent either classes or numbers between 0 and 1, that are either 0 or 1. He calls this the law of duality, sometimes the fundamental law of individual symbols, so the letters. But note that, of course, complex expressions do not always formally satisfy this identity. So if x and y are literal symbols, and you compute x plus y squared, and you do the computation, x squared plus y squared plus 2xy, and then you apply x squared equals x and y squared equals y, you get x plus y plus 2xy, and this formally is not the same as x plus y. So this does not, you do not have this identity. Now, Boole's idea, and maybe it'll get clearer later on in the talk, maybe it's not immediately clear. Now, his idea is that this identity will be satisfied formally if and only if the expression is independently interpretable. Independently interpretable for him here, he's only he's a bit loose on whether it's an implication or an equivalence, but he actually considers it an equivalence later on. It will satisfy the symbolical law v times 1 minus v equals 0. And here, this is a formal equality. You shouldn't take into account what the values of the x and y are.
But if in this form we assume that x and y are disjoint.
Yes, then it works. But this is here formal identity. And then this is actually the most, for him, coming from what we might consider 18th century analysis, it's more straightforward to deal with the formal identity, but then he will try to extend this account to the other cases, and then you will see this coming up again. It should be clear already that here, and I've said this already orally, independent interpretability is invariant under Boole's algebraic transformations. The fact that v times 1 minus v equals 0, if you do this kind of shuffling around, it will not change it. And that's the criterion he uses. He calls this the condition that characterizes independently interpretable logical functions, something like that. And then he goes a step further. And here I want to emphasize interpretation here is no longer limited to the assignments, bottom-up, or even using global properties of expressions, of classes to expressions. He offered a general method based on what he called development to interpret any equation, even when the expressions occurring in it were not interpretable in any of the senses discussed so far. To understand his method, let's consider, for simplicity, functions of two literal symbols, x and y. Relative to x and y, the universe of discourse can always be decomposed into 4 classes, xy, x, 1 minus y, 1 minus xy, and 1 minus x, 1 minus y. This is just somewhat anachronistically, but maybe since we're running out of time, this will be quicker. This is what Venn devised his diagrams to do. This was their initial purpose. So you could have the region, things that are both in x and in y, if this one is x and this one is y, things that are in both, things that are in x but not in y, things that are in y but not in x, and things that are in neither. So you can partition your universe of discourse into these 4 things. And then Boole's strategy, which is patterned upon the development of functions in power series, is to express any function f x y in terms of these 4 constituents. So in blue, I have put the 4 constituents in question that are these 4 regions, and then he obtains through formal methods. Initially, he derives this from Taylor's theorem. These coefficients, which correspond to plugging in 1 and 0 in the arguments of the function, he gets this expansion. And again, this formal expansion does not depend on the particular form under which f is initially presented. Okay, so maybe it will be clearer with some examples, and then I will explain how he uses it. So if you take x plus 1 minus xy, an independently interpretable expression that represents the union of 2 arbitrary classes x and y, you will compute the coefficients here. The 1 you will obtain because it's xy, so you plug in 1 and 1 in the function. If you have 1 here and 1 here, here you have 1, and here you have 0 times 1, so you get 1, and so on. You compute the other coefficients in this way, and you obtain xy plus x, 1 minus y, plus 1 minus xy. And so this is the union of 2 arbitrary classes x and y, and as you might expect, you obtain the sum of these 3 constituents. And in the same way, now, if you have a subtraction, this is an expression that is not independently interpretable because you need a condition. Here, some of the coefficients will be different than 0 or 1. Here you have a negative coefficient that appears. If you put 0 for x and 1 for y, you get a -1. And for the sum, you might get a 2. So you can get all kinds of numerical coefficients here. Now, what Boole says is that the function will be independently interpretable. It will satisfy his relation if and only if all the coefficients are either 0 or 1, which he then checks after the fact. And if there are coefficients other than 0 or 1, as in the case of the two expressions x minus y and x plus y, the function will not be independently interpretable, but, and that brings us back to your point, it brings out the conditions required for the function to be interpretable. Why? Because you want the coefficients that are not 2 or that are not 0 or 1, so the other integers like 2, the negative numbers, and so on, you want them, the corresponding region to be 0, otherwise it makes no sense. So if you want it to be interpreted, you need to kill those, and so you need to get, for instance, here xy to be 0. And then this allows Boole to interpret any equation between logical expressions. So if you have an equation v equals 0, for instance, you develop v. Then interpret, sorry, this is wrong. Then interpret the equation v equals 0 as stating that all the constituents in this development that have coefficients other than 0 are to be separately equated to 0. So I will.
Method of indeterminate coefficient, fantastic.
Sorry?
Is the method of indeterminate coefficient.
Yeah, so it inherits this analysis thing. It looks like algebra in a more modern sense, but it's not. It's 18th century analysis. So if you have x plus y equals 0, then you will have, you know, the full development. You will have x1 minus y plus y1 minus x plus 2xy equals 0. And so you need the 2xy to be 0. You need xy to be 0, otherwise it does not make sense. And then you can get that this is equal to 0. So you get actually two equations. You know, you want xy to be 0 for this to make sense, and then you want these two things to be 0 for the equation to be true. Okay, so I had put another example on my slide. Let's not do it. So recapitulating all of this material. If you consider expressions in two variables, x and y, for simplicity, with no division. Some you can assign classes to compositionally for any assignment of classes to x and y. So those are both immediately and independently interpretable in his terminology. You can do it compositionally, so it's immediate, and it does not depend on any conditions on the classes. Some you cannot assign classes inductively to, because, for instance, here x plus y minus 2xy, you do not know what minus 2xy might mean as a class, but you can still assign them classes for any x and y by development, because the development will give you an expression that is compositionally interpretable. It's a sum of disjoint things. And so such expressions are independently interpretable, but not immediately interpretable. So he will call them interpretable sometimes in some sense, but not immediately, but independently. And then some expressions need some conditions. And then the development, it's a process of interpretation, but the process of interpretation amounts to bringing out the conditions that you would need for it to be assigned a class. And then this allows interpreting any equation. For instance, again, w equals x plus y. Well, you need xy to be 0 for the equation to make sense, and then you can obtain another expression, all of whose sub-expressions are immediately interpretable. Okay, now, further point, in the Little Red Chapter 10 of the Laws of Thought, Boole explains how to alter his method so that all expressions appearing in it formally satisfy this equation. So he doesn't say, I'm making everything interpretable. He never writes that in the book. But given his definition, this means you make every sub-expression in your method independently interpretable. And this will require eliminating or doing something with the step that I mentioned before, where you add the equation. This you should not do naively. So he has all this discussion. In a sense, he does not even need expressions that are uninterpretable in the stronger sense. So they might be uninterpretable in a more indirect sense, because they're not immediately interpretable, maybe in some cases, but they are all independently interpretable. And this actually helps clarify some of his Sibylline pronouncements. So here is one from a later manuscript. One observation yet remains, he writes, there are perhaps no cases in which that freedom from dependence upon conditions of interpretation, which his PSR, what I called his PFR, sorry, for principle of formal reasoning, claims is really necessary as a condition of arriving at results of thought. So there are perhaps no cases in which you really need this principle. Maybe you can always dispense with it and always go only through expressions that are interpretable. It may be regarded as certain that all legitimate consequences of reason may be obtained by a procedure of thought, which, while governed by formal laws, never transgresses any actual conditions of interpretation. The freedom claimed is therefore valuable partly for the practical convenience which it secures, partly and perhaps chiefly because it practically illustrates a great mental law. And I will come back to this. So he thinks it's, yeah, this is kind of maybe strange. But so he thinks the principle is very important. Maybe it's not indispensable. And in fact, in the laws of thought, it's not indispensable in this sense because of what he writes in chapter 10.
What do you mean great? Great mental law, say great.
Great, essential, important, crucial, magnificent, I don't know.
Great mental law.
Yeah.
Great law.
Okay, I think I'm not so great with time. So maybe I'll skip something. So the idea that it was permissible to reason symbolically without regard for the immediate interpretability of the intermediate steps of one's computations, what I call his principle of formal reasoning, it was very important. It's a great mental law. It certainly gave Boole a license not to dwell on such questions as the meaning of the operation of division he used, even though that bothered him a lot later on in his manuscripts, and he would attempt to fix it. However, one should not jump to the conclusion that his method relied on uncontrolled or heuristic symbolic manipulations that were accepted only because they led to apparently correct results. In fact, he did control his symbolic manipulations through his process of development, and he called it himself interpretation. It's not an inductive compositional kind of interpretation, but it's going through these normal forms, if you wish, canonical syntactic forms that he obtained this way. And maybe I just want to add, and maybe I'll be a bit short on this, together with Dirk Schlim, this part is joint work. We have been looking a little bit at not just the authors that are best known in the reception of Boole, but as many people as we could find who wrote about it at the time. And here it's clear that an assessment such as Dummett's, who insists on the fact that you cannot, make sense of his manipulations because you cannot compositionally assign classes to things. This is in line, relatively speaking, with Schröder's rewriting of Boole later on, which is the source that is most read or has been most read later on and has most influenced later readings of Boole. But if you start looking beyond Schröder, it's not so clear at all. Jevons' criticism, so it's well known that Stanley Jevons criticized Boole's methods, and he has a well-known quip about Boole's dark and symbolic processes because his methods seem very weird. And so usually people think, oh, this is because the expressions are not interpretable. He has these divisions that make no sense whatsoever and so on. But actually, if you look at Jevons's actual criticisms, they are quite different from the Dummett concerns. He doesn't care about addition, for instance. This is not something he's worried about. And if you look at lesser known reviews or commentaries on Boole, it seems even clearer that people had no problem with this. Addition and subtraction do not worry these authors at all. Boole's idea that interpretability can be a global property of expressions, you just need to shuffle the terms. This is not something that I see anyone really raising as a problem. They think that's fine. And then actually made a whole deal out of the techniques without even flagging it, but he used the techniques in Boole's chapter 10 in his textbook, and it's rewriting that emphasizes that aspect there. On the other hand, division is a concern, but from a more limited perspective, people say, yeah, we would need to understand, what the division operation does, but it's not about problems with assignments, direct assignments of classes to expressions. It's something more. So I've given a list, but let's skip that. So now maybe I want to come back a little bit to Boole's philosophy of algebra, and I think I have time to do that. I've mentioned this great great mental law, what I call the principle of formal reasoning. So why does Boole maintain that the validity of a conclusion does not depend upon our ability to interpret the intermediate results, as long as one obeys the same formal laws that obtain in immediately interpretable cases? There are various justifications in his publications and manuscripts. He came back to this over and over again. In the laws of thought, the most prominent is the law of the mind justification. The great law of the mind was from manuscript, but you find similar things also in the laws of thought. But then he clearly felt that people were not convinced by this. And he tried various other justifications, saying, well, you could look at it by induction. Just this means, well, you see, just look at mathematicians. They're doing algebra all the time, and it works just fine. This shows that you can do this. This he doesn't put a lot of emphasis on. And then there's a justification by reinterpretation, which I'll skip today, which is very interesting because you see that he's really not thinking in terms of modern models, because he doesn't hesitate to shift to use one model as a way to legitimize the computations that you're doing for another interpretation, even when one is not a part of the other, or there's no isomorphism or that kind of thing. It's very interesting, but I will skip it here. So what is this law of the mind stuff? He writes sometimes the PFR rests upon a general law of the mind, or is founded in the very constitution of the intellect. This is from a manuscript. But how do we recognize it as such? In the laws of thought, Boole implicitly referred back to a distinction he made early on in the laws of thought. He distinguishes the law of nature, which we know by induction, so we observe instances, or maybe they are hypotheses we make to explain phenomena. He has a little discussion of this. And then the laws of the mind, which he interprets in a normative sense, explicitly, it's not a descriptive sense. Those that general truth is seen in the particular instance, and it is not confirmed by the repetition of instances. That truth is made manifest in all its generality by reflection upon a single instance of its application. And he gives as example, maybe x squared equals x, but also things like Aristotle's dictum de omni et nullo. So the fact, the basic principles that ground the syllogism, if you think about it, you will see them. And Boole's move was to place the principle of formal reasoning in the latter category, together with such basic laws as x squared equals x. And he wrote, for instance, knowledge of the principle of formal reasoning is derived, like the knowledge of the other laws of the mind, from the clear manifestation of the general principle in the particular instance. A single example of reasoning in which you do this seems not only to establish the validity of the particular application, but to make known to us the general law manifested therein. So this has attracted criticism, and so it is also why he felt the need to justify the principle in other ways, but he continued to maintain that there was something like a law of the mind. So I want to try and maybe, I don't know if I will fully satisfy anyone here about what this justification does, but I want to emphasize that there is some kind of Kantian undertones here. This is a bit hypothetical, and I will show some other potential sources. Why do I say this? So first, I want to mention a caveat, which is that Boole, although he does discuss Kant in a few places, often implicitly, but sometimes even explicitly, it's not very frequent. But I want to emphasize that this might partly be due to some of the context as well. So here's a funny thing that I found when looking at his drafts. In one of the chapters, he uses Kant's vocabulary of analytical judgments, for instance, to ground his, explain what he's doing. About logical expressions. But then in the last draft, you see the person who annotated the manuscript, who is very likely the Reverend Dixon, a friend of his, whom he sent the manuscript to for comments. The commentator said, I would leave what Kant says out, deleted. And then you see Boole duly deleted it. And you have other, indications that among his close associates and friends, people thought this was an obscure German thing, and it was better not to talk about it. And there are some indications there. So he doesn't talk about it a lot, but certainly he talks about it less than he would have been inclined to, I think. And then you have various elements. So in one manuscript fragment that does discuss Kant explicitly, Boole described the laws at the basis of his algebra of logic as the very laws in accordance with which alone thought is possible, so conditions of possibility of knowledge. In the laws of thought, a few lines after describing the principle of formal reasoning as resting upon a general law of the mind, he concluded that principle, though not as a conceive warranted by formal reasoning based on other grounds, seems to deserve a place among those axiomatic truths which constitute in some sense the foundation of the possibility of general knowledge, and which may properly be regarded as expressions of the mind's own laws and constitution. So there's this idea, maybe it would be overblown to call this a transcendental argument, but it's kind of, this is the principle we need to accept to explain how algebra is possible. It's kind of the line of reasoning he's taking here. Okay, so how much time do I have, Marco?
The time that you want, no problem.
Officially, I'm finishing at 6, is that right?
Yeah.
6:15 maybe?
Okay, but go, no problem. Finish your presentation.
Maybe in conclusion about this Kant thing, I don't want to be too positive about the various sources. There are discussions with Hamilton and Hamilton's brand of Kantianism mixed with other sources. I think this is a work in progress for me to try and better understand if there are things to be said about this or not. However, this is the direction I think he was taking with this law of the mind talk. Now, in conclusion, or in the last part, I want to address readings of Boole that use this uninterpretable language to portray him as some kind of instrumentalist. So this is one reason Boole's explicit defense of uninterpretable steps has attracted philosophical attention. It seems to point to instrumentalism or formalism. Here I'm referring to Detlefsen. I'll show you a quote in a moment. The idea is that, well, it points to an attitude on the part of Boole that is something like the intermediate steps of a computation do not need to represent anything as long as the final result is meaningful and correct. This is kind of the potted version of the view. And Detlefsen, in his discussion of formalism, or what he called symbolic formalism, notably groups Boole together with Peacock, who was not so immediate a source of Boole, and other British algebraists of the second quarter of the 19th century as early representatives of what he calls symbolic formalism. And this is how he defines this position. So this is a quote from Detlefsen, 2005. The instrumentalist conception of language allows for purely symbolic uses of signs in our reasoning, uses that do not depend in any essential way on the semantic content of the signs involved or on their even having such content. This is the central doctrine of the position I am calling symbolic formalism, or more simply, formalism. The central doctrine is itself composed of two key elements. The first is what I will call the creative or creativist element, the idea that the mathematician is free to introduce or create methods out of considerations of convenience or efficiency, as distinct from evaluation of content. The second is the distinctively symbolic element, namely that non-semantical uses of signs may, at least on occasion, constitute such conveniences that you can create for reasons of convenience or efficiency. So that's his definition. Very much in Detlefsen's style. So first I want to address creativism. Here is how Detlefsen characterizes the creativist part, and this is with reference to Peacock, and he explicitly groups Boole together with this. For Peacock, writes Detlefsen, the laws of symbolical algebra were not read off a subject matter they were intended to describe. Rather, they preceded any such interpretation and indeed determined it. This idea that the laws of symbolical algebra are essentially assumptions or postulates that precede any interpretation or definition of the quantities and operations with which they deal is what I will call the creativist element of Peacock's viewpoint. So I will not enter into the question of how faithful this is to Peacock himself. So let's here take this on faith. but think about Boole. So the position, if I rephrase it in my terms, the idea is that the mathematician is free to come up with systems of laws, so calculi in Boole's sense, independently of intended interpretations. And then the laws in question constrain their potential interpretations. So if you do a calculus with x squared equals x, then only some interpretations are possible. However, given the fact that most arbitrary systems of laws would be useless, one needs guidance. You know, a mathematician can create many algebras that are good for nothing. And this is the role that Detlefsen ascribes to Peacock's principle of permanence of equivalent forms. So I haven't brought this up here, but basically he assimilates it to what I called Boole's PFR. For him, it's kind of the same thing, which I think is not true at all. The role of this principle is that it pragmatically directs mathematicians towards fruitful systems, namely those that substantially conserve the laws that hold in arithmetic. So the idea is you can create many symbolical laws, but basically what you should do is take the laws of arithmetic and then remove restrictions. Typically the kind of example that we've seen. Actually, he wrote it with Z and Y reversed. So this is why people see a similarity between the two things. You can have a law like this, which is valid when Y is smaller than X, and then you say it is valid in general, and then you get a more general kind of algebra. All right, so that's the view that Detlefsen ascribes to Peacock. So I want to say first that Boole was not a creativist in this sense at all. Boole held exactly the view that Detlefsen denied of Peacock. Symbolical laws were not freely created, but read off. He is very clear about how he thinks symbolic reasoning should go. The first step is you decide on the interpretation of your symbols. For instance, you say that letters would stand for classes, the sign plus for disjoint, the aggregation of classes, and so on. And here you have freedom. And here you can follow pragmatic considerations, but you have to decide on what the symbols mean initially. Then you describe the laws that govern the symbols when everything is interpretable, for instance, such laws as those. And it can turn out a posteriori that different domains are governed by the same laws. And so you have the same calculus for classes or for numbers that are either 0 or 1, when letters are numbers that are either 0 or 1. And then you have the principle of formal reasoning, which allows you to use these laws even in cases where immediate interpretation is not possible. And this guarantees that you can do this. But there's no creation here out of considerations of convenience or efficiency. Once you've decided what plus means and what the letters mean, the laws fall out of that. And then you can follow the laws even in cases when it's not immediately interpretable, but you're not creating a system out of convenience or efficiency. The PFR of Boole is not like the principle of permanence in restricting for reasons of fruitfulness which systems you could entertain, but it's just about allowing free rein to algebraic manipulations once you already have your formal laws. It's a very different perspective. Okay, so that's about the creativism. But then Detlefsen also insists on the symbolic element, which is that you can use non-semantical uses of signs. And this, it seems, at first sight, it's much more promising. You think, well, Boole repeatedly describes language as an instrument, not just a medium for expressing things, but an instrument for reasoning. Moreover, he maintains that language's effectiveness as an instrument for reasoning and solving problems does not depend on our attending to what the words and sign mean, as long as we obey the relevant formal laws. So you can do the PFR thing. You can stop worrying about the intermediate steps. So at first sight, he endorses Detlefsen's non-semantical uses of signs, but these are not mere conveniences. It's not for pragmatic reasons. And the key difference here, I think, is in how Boole justified the detour through uninterpretables. A typical instrumentalist position would just say, well, look, it leads to correct results. Either I observe that the method works, or I give a kind of general proof in the Hilbertian style that this works, that the whole system is consistent, for instance. And this would be how it's justified. Boole instead relied on his PFR and says, oh, this is founded in the constitution of the intellect. It's a condition of possibility of algebra with this kind of Kantian undertones that I've looked at. So I think in spirit, it's very different from an instrumentalist position. Okay, I had one slide discussing whether this was a terminological issue, but I think it's better to have discussion, and I will show it to you if this comes up. So just to sum up what I've said, I've complained at the start that discussions of Boole's uninterpretables typically project onto his texts the standard notion of interpretation, compositional interpretation from first-order logic. And this has a lot of unfortunate consequences. It mixes modern concerns about the addition and subtraction, like Dummett complained about, that did not worry Boole nor his immediate successors at all, together with issues of immediate concern for them, such as division. It confuses Boole's various notions of interpretation, and therefore it tends to equate uninterpretable with meaningless, even though Boole does control all his expressions semantically through his process of development that gives them a syntactic normal form. It assumes that justifying his methods requires actually providing interpretations to all the symbols, like in Hailperin's method. And then it tends to lead to an instrumentalist reading of his relation to symbols. And I've tried to say that the views of Boole are actually much richer and much more interesting than this. His approach to algebra, which is based on a kind of normal forms on the model of series developments, could actually be used to justify his calculus instead of using multisets. And actually, there's one paper in the literature that tries to do that using formal polynomials. As for his account of algebra, maybe no one will be convinced by it today, but I think it's a creative and original effort that tries to draw on philosophical ideas to solve the kind of methodological issues about algebra that he had. And I think that's interesting in its own right. Okay, thank you very much for your attention. And we have time.
Okay, so we can discuss. Remember that for him is a very big problem to go to a business and do for us, no, but for him, it's terrible.
It's because you interrupted me, Marco, of course.
Sorry?
It's because you interrupted me, Marco. Of course, of course, of course. No, no.
Then and then German, okay? Or German. Then.
So independently interpretable means in principle or ultimately, and immediately means as
Now
it is given.
No, so independently means so immediately is as is it given, or usually the way he uses it, I think, is what he means when he says immediately or in interpretable form. I think I have my little recap that will come in handy here. Okay, so immediately, yes, you can do it as it's written compositionally. Then it could be independently, strictly speaking, it means that you do not need further conditions. So x plus y is not independently interpretable. So it's kind of orthogonal. Why? Because here, if x and y are interpreted as disjoint classes, then actually you could interpret this immediately. So the question is it do you need further conditions like x, y equals 0? So the condition that they are disjoint. If you don't, then it's independently interpretable purely formally. If it is, then and then you have expressions that, yes, that are interpretable only if they satisfy certain conditions. So I guess it's a bit orthogonal. I mean, it is two different things, but independently, the reason why they seem to be linked is initially independently interpretable because it is a formal notion, is the one that Boole is most directly able to phrase as a global property of expressions. So if you have no condition, it's straightforward using development to bring it into an immediately interpretable form.
Okay.
If you need further conditions, then you do development, and then the development brings out the conditions, and then
you apply.
Yeah, and then you have the conditions, and then you say, well, if I set this to 0, then I can immediately interpret it, something like that.
So, thank you.
Gemma.
Thank you for your talk. And for raising the question of interpretability for different authors, which I hadn't thought about precisely to be quite different. What this reminded me of, because I was thinking about it a lot, is analytic geometry. And the last step of analytic geometry in Boole's time is to take something, a result in algebraic language, and interpret it geometrically. And I wondered, does he refer to analytic geometry at all? Is this something that is, and and sometimes in the intermediate step, there's no demand for interpretation in analytic geometry as well.
Yeah, so I mean, I guess that depends how strictly you define analytic geometry, but clearly it's very much in the background in the sense of so I've suppressed this part, but there are clear indications that his immediate source is Gregory. So the references to the trigonometric thing, the language he uses, sometimes direct quotations, although that's rare. And so if you look through the Cambridge Mathematical Journal, you have all these papers by Gregory around these issues. And so I think it's an important context in the background of forming the idea of the relation of the calculus and the interpretation. It's also, so I think one of the, so pity I don't have the quote on the slides, but there are nice quotes that I think are a good background for also what Boole is doing in this kind of indirect interpretations. Gregory is very explicit that interpretation can be quite open-ended. So he has examples. He says, well, I think this is about products, the kinds of calculi. So what Gregory does is a bit weird. It's not like standard analytic geometry, I would say, but it's clearly trying to use algebraic techniques for geometrical objects. And so he has quotes where he says, oh, here is a way of interpreting a product of 3 terms, and here we can do it in 3 dimensions, but maybe later, maybe with more terms, we can't interpret it, although maybe we will figure out a way later on. So it's kind of this open-ended process. And he has several passages like this, I think are, it's not a fixed thing and you can come up with new things. One passage that is more closely related, but I think I have no idea whether Boole even read this, so I don't, maybe this is not relevant in this connection, but the text, the published text by Babbage, where he talks about the interpretation of analytic results, that's called notation or whatever, I don't remember what the title is. There, he is very explicit about indirect interpretations that are not assignments of objects to the expressions. For instance, how you interpret an expression to mean that maybe the problem is impossible in certain cases, or all the various ways you could do. And usually he does not use the language of interpretation, but there are some passages where he does. I'm dubious that this is directly related, but it could be. So, and certainly many people were using interpretation in all these ways at the time. I don't know if I can, but if you have interesting, useful references in that of that kind, I would be interested.
I guess just related to the slide, one of the slides you skipped about the reception, were those working in geometry more receptive to his work? By any chance?
That's a good question. Usually, I mean, many people were, that's a good question. Well, do I have, I didn't find so many sources so far. So I'm also interested in, wait, I skipped it. I went way too far.
I think it was like in the 30s.
Okay, well, it's at the, I'm kind of scared by the thing, so I don't want to break it by opening the thing where I can jump. I think it's here. So not that many people wrote about it that I have found. So here are some that I found interesting for one reason or another. Cayley uses geometry in his, I showed some of that. De Morgan, I don't really know here. So these authors, this Paxton, George Paxton Young, was I was not able to find a lot of information on him. Was an inspector for grammar schools in Upper Canada and wrote in a Canadian more local publication. And it's interesting to see how he processes it, and so has no problems with some of these things there. Harley is very close to Boole. One interesting case is Hasted. So actually parallel, you might know him for precisely other kind of work. So this is there are like maybe 3 papers from the late 70s where he goes into this, and has some close parallels with what Venn is doing, even though Venn does not have that kind of mathematical background. So I think it's a good question. So maybe you would want, maybe Halstead would be the first suspect to look at there if you want to. Yeah. If you find other sources, I'm very happy to take them.
So I have a question about this main law of the PSR.
PFR, yeah.
PFR. And so you want to read it, you want to take seriously this remark about it's a law of the mind in a Kantian direction.
Yeah.
But you mentioned other justifications, who is talking about too. Now you distance just your interpretation from one that sees it just as a kind of instrumentalism or formalism, where all that matters is the consistency. But what about the consistency issue? Does he think he has given an argument for consistency? Maybe he wants more, but it's also a condition of possibility or something. Yeah, but what about the consistency?
Yeah.
That's my question too.
Okay, yeah.
There's no negation on this. Right?
Sorry?
There's no negation, right? It's just equations. The laws prove equations.
Yeah.
You can't really, so I was thinking about this during the talk. The one thing where inconsistency would come up is just triviality. You can prove everything.
Yeah, I mean, you could end up with this. Like,
right. So, so my question would be, is he concerned with that? And also, the way we would understand that doesn't happen is by giving a model where what's on the left is not on the right. But so then my question is, I'm sorry, I'm taking up the time, but then my question then related to your question would be, how does he know, or he must have some criteria when he knows that two expressions are different.
To add, just to my side of the question in a way. So you want to read it as it has to do with conditions of possibility of doing certain things, but that's only work if it's consistent, or there isn't a problem in a way. It doesn't lead to some problems. So that's more the other side of it.
So, yeah. So I mean, I think he doesn't think of this as maybe an axiomatic system where the question of consistency is so clear cut. So you could get contradictions like this in some cases, but well, the question is, you have these laws, but then I guess he doesn't doubt that the laws are consistent in some sense, but the laws are not what you actually are working with. What you're working with are you have the laws, but then you also have your hypothesis in a given problem. It's totally possible that you get this in the spirit of getting a reductio. But this indicates that you have to suppose that the universe of discourse is empty. Basically, it's impossible to have the conditions that you've laid out. And the fact that he sometimes seems to be reasoning in this way certainly suggests that he doesn't, it's not for him even conceivable that the pure calculus itself could lead to this kind of thing. What could happen is, the pure calculus itself is you just have these rewriting rules. In a sense, you're not starting with anything. And so I don't see in his frame of thinking how he would formulate the problem of consistency for the calculus itself. I don't know if that have to think some more. I mean, this definitely can happen, but again, you have starting points where you have actual equation that you're starting from, and then you're using the laws to rewrite them. And then he will consider that the problem, if you get to this, is that the conditions you put initially were not consistent with one another. But the mere rewriting rules, he doesn't really ask this question in this way, I guess. Does that make sense? Or
Yeah, I just was wondering the criteria for distinctness.
oh, the criteria for distinctness of
Like in with one of Jose's questions, you had x plus y plus 2xy, not equaling x plus y.
oh,
What's his criteria for saying that those two things are equal?
mm-hmm.
Maybe we can be really clever and come up with some derivation by his laws that make them.
Oh, well, so I guess in that case, you could say, yeah. So I understand that here you might want to say, well, we might look at an interpretation. And we
Right,
might.
Is that too modern or is that something you?
I'm trying to think if I have good reasons to think that the question would have fully made sense to him, like in the abstract formulation of the calculus, are they equal or not? Like I've used it here to pedagogical reasons, but is it obvious that he would have thought in this way, that he would have asked the question in this way? I'm not sure. I mean, certainly I wouldn't be surprised if you had asked him and he would have said, well, look, if you take x and y are 1 and 0, you get different answers. And here the operations, you can do the operations. Yeah, I mean, one thing I agree that is unsatisfactory for that reason. So he doesn't raise this question of he doesn't seem to entertain the possibility. He presents the PFR as a general principle, and you can always do this and abstract away from these conditions. He doesn't seem to entertain the possibility that actually, if you do this for some kind of calculus, you might get to inconsistencies. I think, and that's, I mean, from our perspective, it is very unsatisfactory for that reason, because yeah, we might. I think I agree with that.
Yes, in relation with these questions, I think that even though he speaks about a function and he means what we would call a term nowadays, but still I believe he's thinking about a functional equality between terms. He speaks about this canonical representation.
Yeah.
And the fact that he uses Taylor series or Taylor's polynomials in order to find equalities between terms goes in this direction.
Yeah, functional, but functional. I mean, you can ask Marco, who is the expert on what this kind of equality might mean in the context of 18th century analysis. But it's certainly not the input-output thing. Will they have the same value for all cases? It's a more formal thing.
Maybe not all cases, but maybe in the relevant cases.
Yeah, but so what's the relevant case?
Probably 0.1.
This is exactly the question, the point that I wanted to make. It is an interpretation of interpretation, as I can say. Yes. It is something that does not surprise me at all, because it simply that is a perfectly continuity with Euler-Lagrange composition that is important in England in the end of the 18th century. And make an example. Take the expression, this one, and you develop into a series, and so you have in development, and then you take x equal 1, and you have the grand series. You have that is one happening, etc. So our interpretation is, oh, this is wrong. This is true only when x is smaller than 1. So this is not correct. But for Euler and Lagrange, this is not absolutely the case. This is perfectly correct in any case, but as a numerical value on the surface. So if you want to interpret this expression in terms of a numerical calculation, so you have to introduce limits on the value of x. But if you interpret this as a formal transformation, the fact that this came from this by certain rules, then this is universal valid. So the notion of convergence is not a condition a priori of the validity of the identity, is a condition a posteriori of the applicability of the development to a certain case of interpretation. Okay, so this is a general way of thinking it all 18th century, and it seems to me perfectly in this perspective. But you are right on a point. This is a correct correction only if there are a small interval of x, small or big, but there is an interval of x in which is numerically valid. So it does not need to be numerically valid everywhere, but it should be numerically valid somewhere, because otherwise this transformation cannot be appropriate. Okay, so it seems to me that is exactly the way of thinking.
Yeah, I think that's absolutely right. And Boole's first papers in mathematics were in that vein as well, very much so. I should add maybe one point to that, which is this question of the role of the quantitative interpretation for him. Because on the face of it, and this is linked to his justification by reinterpretation, which I have skipped, but is conveniently on the slide here. Why would we care that the numerical case and the class case have the same laws? Why would we care if it's just the uninterpreted calculus governed by the PFR that counts? And in one way, he presents it sometimes in his later manuscript as a heuristic thing, because we have all this developed, analytic results that we can then transfer, and we don't need, they must be just based on the laws. Well, if you set x squared equals x, so you eliminate all the higher powers, but then they're just based on this, and so we can just transfer them. But maybe there's, there was a sense, especially in his earlier work, that what happens in analysis and the fact that Taylor series might be related to these considerations kind of gave an additional warrant to the use of, even though he moved away from that in his later manuscripts. But so there's certainly this question there. But yeah, I think I agree with Marco. It's like an effect, I think, of reception that most people who have written on Boole, even who have read Boole, have not read him in this context there. And so
I read the Boole in the context of arithmetization of analysis. That is a process that is developed after Cauchy in France and in continental Europe. That is absolutely not what is happening in British mathematical.
Yeah, or other things, because Schröder was so important.
Sorry?
Schröder was so important. And he comes from, another background, that from Grassmann and that kind of things that he has
Sorry. Schröder is what is the chronology of Schröder?
It's late. Schröder, the first thing that Schröder publishes on Boole is 1877.
Ah, no, that okay. No, I'm thinking on the first half of the 19th century. Then in the middle of the 19th century, something essentially is changed.
Yeah, but so when people read Boole, yes, and so Schröder reads Boole, irrespective of the analysis thing, the way what he assumes about what interpretation should be comes from somewhere else, and usually people have, after Schröder, mostly have read.
So Boulos, the Boulos. Boulos is another one. Boole formation is, if I remember well, is in the context of analytical society. So,
yeah, kind of. I mean,
no?
yes. I mean, he's kind of self-taught, but yes, he was in contact with these people. So, I mean, I want to make too strong assumptions, but about the cohesiveness of the thing. But Gregory, how much he read, how much he fully was working with Peacock's saying is not so clear to me, but certainly Gregory and yes, and his first paper, the general method in analysis, is very much in the spirit of calculus of operations kind of thing as they were practicing it. But his view with the PFR is kind of idiosyncratic, so it's still kind of.
So I find it super interesting with this, also what Marco just explained again. So like, if we could rewind history and say like, so modern logic, right? So we were kind of redoing it, not with our modern notion of interpretation, but with the notion of interpretation, which kind of is inspired by this. How would logic look like?
I don't know. I don't know. I don't know. I don't know about logic, especially as I don't know how much this kind of thing had an impact later on, but what can I say?
What the point that you want to make?
Okay, so let's just look at equational logic, right? So equational logic.
Yeah.
Okay, so that's how I know Boolean algebra, right? But this is totally different.
Yeah.
Right. So we cannot understand Boole's algebra using our ordinary universal algebra equation logic that we're doing today, right? But it could still be that there is something we could replace universal algebra with that is able to account for Boole's algebra. What would that be?
No, so you can't. So I think these are two different questions because if you look at a mathematical reconstruction like Hailperin's, it's a way of making sense of what he's doing in our framework.
But you convinced me that Hailperin is kind of forcing Boole into our framework and not really doing justice to it.
Yeah, well, so one way you could go is the way Brown is going. This is a kind of, I don't know if many people have read this paper. It's a paper in the Notre Dame Journal of Formal Logic, I think, probably by some retired mathematician, or I'm not sure really who he is, who said, well, you could do it, the multisets, that's fine, but you could do it with formal polynomials as well. So you could use algebraic tools that are more from formal power series, formal polynomials, that kind of thing. You could do ideals of rings of polynomials. You can do things by staying in a very much more formal expression based framework without trying to. I mean, mathematically, there isn't a huge, you could get correspondences between the two things to a certain extent, but it's different in spirit from kind of creating a formal gizmo, set theoretic gizmo like this to interpret the expressions. You can say, well, in a sense, you have these rewriting rules, and you could say that the semantics of an expression, in a way, is the form you can get to by these transformations, or maybe the equivalence class of expressions, or something like that. And this is more in line with, rewriting systems in computer science, so that kind of thing. So I think the more substantial answer would be you want to go in that direction, where you have something that's more like, I don't know, operational semantics in computer science as opposed to the notational one. I don't know, maybe that's would be one answer.
One thought I had, this might be related to what you're saying, but there's a notion of a canonical term in constructive logic. A canonical expression. Do you see the
like I'm not like if you do lambda calculus, for instance, you have like the normal form you obtain after reduction. Is that the kind of thing you're referring to, or something that I don't know about? Maybe
some of the people in this room know that thankfully, but with isn't there a notion of a canonical expression or brackets?
Like in classical representational logic, there is a disjoint normal form.
No. But David doesn't.
And it's not the disjunctive normal form that you're talking about.
It's a notion in constructive logic.
Okay, probably I don't.
Peter, I was waiting for your.
I have a comment here because this is what Boole is doing nowadays is considered partial Boole, partial algebra.
I don't think so. I don't think it's true. Because I was thinking of this, but I
Yeah,
thought that what he was doing was different.
I mean, he's got a different motivation because he's really trying to use arithmetic to do propositional logic. And he knows that he can't get the idempotent law in arithmetic, so he has to have this restriction. So the restriction is basically saying that the drawing is partial. And you can, the theory in which this is handled properly now, they can detect they are the setup in which
So what algebras you say?
the technical that they come up with. I mean, that's it.
Oh,
Probabilistic, it's a partial algebra theory and can be connected to probability theory. And there you also have disjoint unions being the ones that, you know, one consider. So it's interesting that this is where the algebraic version of logic first started, because if you think about what logic was before Boole, it was basically, you know, there was no notion of formula logic. Aristotelian reasoning, syllogisms, and he pointed out that you can have a number of logic. It wasn't quite the one that later on developed into the. It's actually something that you can make mathematically sound in the sense of setting apart.
So that's
I just want to say, because it relates to my question, so it's actually, I can now rephrase my question, thanks to what you said. And so my question is exactly, like, I understood this as being different than effect algorithms, yeah. And that's what I would be interested in, right? So it's not effect algebra. So what is it?
Yeah, and so I would say it's an algebra of a formal series of formal polynomials. I would guess would be my first guess, because if in your partial things, it's just that sometimes things are not defined because the operations are only partial, right? But so can you still compute with the expressions when they're not defined, like Boole does, or does it like prevent you from?
Because it stops. But as you point out, if you rewrite things in a different way, then you avoid the partiality.
Yeah, but so because his way is also.
It wouldn't happen in effect algebra. So I think Alex is right. This is not the same as.
That would be interesting to look at this together.
Yeah.
Yeah, and I mean, my instinct is to say if it's partial, it's not what he's doing, but maybe you can still make a correspondence between them in some way. Yeah.
Okay, okay, two remarks. One question. Do you think that there is some connection to the idea that you were discussing that not all the steps are to be interpretable in the middle with famous Leibniz and also the Descartes idea of blind thinking?
Mm-hmm.
There is a direct connection with that. So Boole is aware that or not. There is no.
I don't think so.
Independent way of.
I don't think so. I mean, I would think not, but
No, there is no connection.
I think not, but however, I never want to discount what Boole may have read. He was widely read and very eclectic because he had no formal training and no formal university training, and he read the books that he could get his hands on. And I wouldn't want to dismiss any possibility, but not that I'm aware
There
of.
is no evidence.
Not that I've seen, but maybe maybe I didn't recognize it. But
Okay, I have another question, but Giselle wanted to tell something about that.
I want to say Javier Legri's chapter on the topic to answer your question.
Sorry?
Javier Legri's chapter on Schröder and Boole and the symbolic, the tradition of symbolic.
But that's he's looking downstream.
Yes,
But that's not upstream. Yeah, okay.
Yeah, but what I just want to refer to with this mention is to say that there's a small discussion in the beginning, so it could, illuminate what we are thinking about, despite we're not talking here about influences, right? Like as in Leibniz influence with his idea, what Boole is doing. Nevertheless, we can see similarity between the ideas. You know, without the influence, we can see operating here. So in this sense, there is a connection. There's no connection in terms of influence, but there is a connection in terms of what's going on.
Because
the conceptual connection is clear. The point is whether there is also a historical connection.
Because you believe that if there is an influence, then it is more relevant than the mere.
No, you have to know whether there are. The other remarks.
I'll look at the reference.
Someone else? No. The other remarks is the following. You convincingly argued that Boole's notion of interpretation is not our notion of interpretation. Okay. But I context that we have one notion of interpretation. And so I think that there are at least two natural ways to interpret interpretation. One is a Taskian way, the way in which interpretation is gained by modern theory, and that's certainly not what is here. I think that what you speak about interpretation, you speak something else. You speak to the idea to assign a signification to symbols. That is not the same thing that you interpret a certain form within a certain model. Okay? So when you say that it seems to me that when you implicitly, when you speak of our notion of interpretation, you are sort of jumping between two ideas. One is the model theoretic notion of interpretation, semantic, and certainly there is nothing like that here. And another is a different notion, more naive, if you want, notion of interpretation. That means that when you write something, you need to mean what does it mean. And that's two different things. Interpretation in the second sense is not the interpretation in the first sense. To make a simple case, of course, in Frege, there is an idea interpretation in the sense of I need to know what does it mean what I write. But absolutely, there is no notion of interpretation in the modern theoretic sense. So I think that what you argued, of course, there is no Taskian notion, but there is either not the other notion, because, or in a sense, so that's my point. What is your position with respect to this idea that interpretation means I want to know what I write does mean?
Yeah.
So I think that in a sense, Boole again.
You say it always.
Agree with the idea that I know what does it mean. Simply, I don't know what does it mean in the form in which it's written. I have to transform, I have to reason, but in any moment of my process, I can tell what I'm saying or not.
Yeah. So So I totally agree with that, and I think that doesn't create misunderstandings so much. So I think the problem is because some of the quotes by Boole do invite the more compositional one. When he says, well, when there are not disjoints, then it seems that this is not it's not interpretable. So it's kind of natural to jump to that thing. And that's where then you get into trouble because you don't understand what he's doing anymore. The idea that he uses interpretation in this loose way to mean, do we understand what the symbols mean in the various things? I mean, I'm not sure I understand your point. So certainly he uses interpretation in a...
I make a very simple example to fit my point.
Yeah.
Okay. You say, okay, one means the universe and zero means the empty.
Yeah.
If I want to interpret it under the point of view of my notion, modern semantic notion of interpretation, I say, okay, the universe can be any set that I want. I can interpret the universe as the natural number. I can interpret the universe as the real number. I can interpret the universe as the member of this class. I can interpret the universe. So I have different interpretation of the notion of the universe.
Yeah.
But that is not the point, because when you say I have a numerical interpretation and a logical interpretation, so it's not that you interpret the universe in different sets. you add a different meaning that is associated to the symbols. It's not the same thing to give a different meaning to the symbols and to interpret the symbol with respect to different models.
Yeah, no, I agree with that. I think what's confusing is that there are elements of both, but I haven't put in the slides, but at some point in the paper, I look at various other ways in which he uses interpretation, and sometimes it actually means translating back into English clearly, and nothing more than that.
Exactly.
And then sometimes he uses it in a more precise sense. In logic, clearly, sometimes he means, well, what class does this represent? Not, you know, how you, but they are kind of.
That's what the idea is present, you think, in some sense.
Yeah. So it's just that it's not the only thing that it can mean, and you can still interpret something when it does not represent a class, because you could, for instance, interpret it by knowing which are the conditions under which it would represent a class. But still, the idea that in some contexts, interpreting would mean that it represents a class that maybe even indirectly, maybe you're just representing the English words, but they themselves, they represent classes. The idea, at least in Nietzsche, it's there. It's not completely absent. So that's why it's kind of confusing, I think, but
okay.
I feel like, you know, I hate going over time. Then I feel like I'm keeping everyone captive, you know, and I don't like doing that.
Other questions?
Mm-hmm.
Feel that.
Yeah.
No. Other questions?
I have to go, but I look forward to reading your paper. I'm glad it's a paper I can read.
Yeah, it's already, I mean, it's not submitted yet, but it's
Okay,
written.
so we can close here.
Mm.
Thank you.
Mhm.